Good morning. I would like to thank the organizers for the opportunity to give this talk. The title is Telephone Numbers, and my name is Diana Avella. Consider the following problem. We have n telephones, and we wonder in how many ways can their owners talk between each other. We are not considering group calls, only phone calls between two persons. This number is called telephone number, and will be denoted by Tn. So in this talk, we will see some ways in which we can obtain these numbers and how they are related to some other important concepts. If there's just one person, he cannot talk to anyone, so there's this possibility. So consider at least two persons. If we have n persons, maybe the person number n does not want or can't talk to the other ones. So the rest, these n-1 persons, can talk to each other in Tn-1 forms. The other possibility is that person number n does want to talk by phone, so he chooses one of these n-1 persons to talk with. Maybe he chooses to call J, and then the remaining n-2 persons can call between them in Tn-2 different ways. So we have here n-1 times Tn-2 possibilities. And the sum of these two numbers equals the number of total possibilities. So we have this nice recursive formula for telephone number. Let's calculate some telephone numbers by using this formula. As I said before, if there's just one person, there's only one possibility. If there are two persons, then they can talk to each other, or maybe they don't want to talk to each other. We have two possibilities. For three persons, T3 equals T2 plus 2 T1, which is 4. And for four persons, we have T4 equals T3 plus 3 T2, which equals 10. So there are 10 possibilities for 4 persons, for 4 telephones. So this formula is useful, but let's give another one by studying telephone numbers in a different way. Let's represent each telephone by a vertex and join two vertices if their owners phone call each other. So if we have phone telephones, we will have one vertex for each phone, each person. And if we put an edge here, we represent that person 3 is talking to person 2, and maybe persons 1 and 4 are not talking by phone. So this graph represents a possibility. In this way, we can visualize all possibilities and write them down. Here we have a possibility, maybe none of these 4 people is talking by phone. Maybe only 2 of them are talking by phone, and then we have these 6 possibilities. Or maybe they are all talking by phone. Maybe 1 is talking with 2, 3 is talking with 4, or maybe 1 with 4 and 2 with 3, or 1 with 3 and 2 with 4. So we have these 10 possibilities. We already knew that T4 equals 10, but here we have visualized all different possibilities. What we have here is a matching of a graph. A matching of a graph is a subset of edges with no common vertices. This one is a matching of the complete graph for 4 vertices, in which we only choose 2 edges, the edge which joins vertices 1 and 4, and the edge joining vertices 2 and 3. We can write it like this. There's another matching with just 1 edge between vertices 1 and 2. So in this way, we can see that the telephone number for n telephones equals the number of matchings in the complete graph for n vertices. With these ideas, we can obtain a formula for telephone numbers. Let's see how many matchings are there in the complete graph for n vertices. One possibility is to put no edges. Another possibility is to put only 1 edge. Then we have to choose any 2 vertices out of the n vertices we have. And this number is exactly these binomial coefficients n and 2. So in this case, we only take 2 vertices to choose an edge. Another possibility is to consider a match with exactly 2 edges. Then we have to choose 2 vertices out of n for the first edge. And then we have to choose 2 vertices out of the remaining n minus 2. So we have this number of possibilities. But if we first choose the edge between A and B, and then the edge between C and D, this would be the same that if we choose first the edge C and D, and then the edge between A and B. So we are counting twice. We have to divide by 2 to get the real number. If we construct a matching with 3 edges, we have to choose 2 out of the n vertices we have, but then we have to choose 2 out of the remaining n minus 2, and finally 2 vertices out of the remaining n minus 4. So we have this number of possibilities. But as before, if we choose these 3 edges, for example, first this one, then this one, and finally this one, that would be the same that if we choose the same edges, but in another way. So we have to consider all possible ways to rearrange these 3 edges. We have 6 possible rearrangements or permutations of these edges. So we have to divide here by 6, by 3 factorial. In general, we see that for T8 edges, then we have this number of possibilities, these binomial coefficients, product of these binomial coefficients divided by factorial of T. So the total number of matchings will be 1 for the possibility in which we have no edge, and all these ones for matchings with 1, 2, and up to m edges. Which is this number m, which is the maximum number of edges we can put in a matching of the complete graph. If number of vertices n is even, then we can have at most n divided by 2 edges in the matching. And if n is odd, we have at most n minus 1 divided by 2 edges in the matching. So this is the value of m. And as we said before, this number of matchings of the complete graph equals the telephone number for n telephones. Let's relate the telephone numbers with a very important concept. We know a permutation of a Zx is a bijection next. We can consider all bijections between this set and itself, And this is called the symmetric group in N elements. It is a group under usual composition. It's called the symmetric group. If we can write a permutation like this, putting an array in the first row, we put numbers 1 up to n, and in the second row, we put the images of this number under permutation alpha. So for example, in this case, we have permutations of number 1, 2, 3, and 4, in which 1 goes to 2, 2 goes to 1, 3 goes to 4, and 4 goes to 3. So we interchange 1 and 2, and we interchange 3 and 4. In some cases, permutation equals its inverse, and these kind of permutations are called involutions. If we have an involution alpha, and alpha sends e to j, then j must be sent to e by alpha. So these two numbers are interchanged by alpha. Let's see an example. If we only interchange 2 and 5, the same permutation will give things as the initial positions of this number. So alpha, it equals its inverse. Maybe we can have a permutation with 2 interchanges. Permutation beta that interchanges 2 and 5, and also interchanges 3 and 4. And also, if we apply once more beta, we obtain the identity. So this is an involution. So it's not difficult to see that alpha is an involution if and only if it is the identity or it is the composition of, let's say, these m permutations. Each permutation interchanges exactly 2 numbers, and the numbers interchanged by some of these permutations are both different from the ones interchanged by the rest of the permutations. So these interchanges are called transpositions in group language. So which is the relation between these involutions and telephone numbers? First, we know matchings and telephone numbers are related. But if we have matching, for example, these 2 matchings, we can think of these matchings as a codification of some permutations. If we have an edge in the matching, we can think that this edge codifies a permutation which interchange 1 and 4, and this other edge is saying that 2 and 3 are interchanged. So we can visualize this matching as permutation interchanging 1 and 4 and 2 and 3. In this case, we only have one edge in the matching, and we can think of this edge as a codification of interchange between 1 and 2. So we can associate to this matching the permutation which interchange only 1 and 2. In this way, we have a bijective correspondence between matchings of the complete graph for n vertices and involutions in the symmetric group. So telephone numbers are in bijection with matchings of the complete graph, but matchings of the complete graph of n vertices are in bijection with involutions in the symmetric group. As a consequence, this telephone number, which we obtained before, is also the number of involutions in the symmetric group for n elements. And there are some other interesting relations between telephone numbers and other important concepts. For example, permutations can be visualized by what we call Young diagrams. And these diagrams can be filled by numbers to obtain what we call Young tableaus. And there's a relation between these telephone numbers and the number of certain tableaus. So if anyone is interested, there are other nice relations between telephone numbers and other concepts. Here are some reference. You can see if you are interested. And that would be all. Thank you very much for listening.